In this video, I will guide you through a problem in Smith's Organic Chemistry. I'm Stoddard, founder of Study Chem, the place for students to turn for higher grades in OChem. Let's get started. This is problem 913. Draw two different routes to each ether and state which route is preferred. You might recognize perhaps this is a Williamson ether synthesis. So the ether is bonded two different ways. The oxygen is bonded to this methyl on the left, and we'll call this way one. We can start with the alcohol, which in this case would have this oxygen-carbon bond already there. So we'll draw this alcohol out, and then we're forming this blue bond here between the oxygen and carbon. So what we can do is we can do this reaction by first treating this with sodium hydride to make the alkoxide, and then we can treat that with CH3Br. Okay, that's one way. It'll make, this compound. I've just copied and pasted it. Now, another way to do the synthesis is, of course, form this bond here. Okay, so I'll draw the dotted line to indicate that we're going to break that apart into our two starting materials, or that's the bond that we're forming. So we can start with the yellow bond already in place, the methanol here, and we kind of do a sequence of events very similarly. We can treat this with Na. Step one would be NaH, sodium hydride. And step two would be this whole creature here with the leaving group. So this would be bromocyclohexane. Okay. So this reaction works by an SN2 always. Okay. Well, it doesn't say how we should make these alcohols, but I'm just going to do it by a Williamson ether synthesis. And remember that SN2 is best for primary or methyl groups, and better than secondary, and better than tertiary. Okay, so sterics is bad for substitution reactions that go by bimolecular nucleophilic substitutions. Okay, so sterics is bad. Now, that means that this guy here is a secondary alkyl halide, okay, and this guy here is a methyl halide. So this ray right here is going to be preferred. Okay, you want the less substituted alkyl halide. Let's do the similar kind of analysis down here. We have this bond right here that can be formed. Okay, and we can do that by taking our alcohol here. So we're going to keep this bond to this carbon. And this is alcohol. And so what we would do is we would treat this with sodium hydride. Always use step one and step two here. And we would treat that then with the alkyl halide of the other alkyl group. This is 1-bromopropane ethane, and this is a primary alkyl halide. Another route that we could possibly use is to try to synthesize this molecule by forming that bond. So we would then start with ethanol with this bond already here. Okay, and we would go through a similar sequence of events. Treat this with first sodium hydride, and then we would add this alkyl group with the halogen leaving group. Okay, so bromine or chlorine or iodine are good leaving groups. I just choose bromine typically. Okay, and this alkyl halide is tertiary because that carbon's bonded to 3 groups. So that's tertiary. That's particularly bad. So the best possible route to synthesize this ether would be by this way right here, okay? And that's using the Williamson ether synthesis. Now there are other ways to make these ethers, but I'm just going to choose to demonstrate how the Williamson ether synthesis can be used. Keep in mind, you want to pick your alkyl halides such that it's less substituted, okay? Less substituted alkyl halides like methyl or primary work better in SN2 reactions. Thanks for watching.